Right, hello. So today we're going to do a problem called Snail on Elastic Band. So the idea here is we have a snail and it's on an elastic band, and one end of it, the elastic band, is fixed to a tree or something else which will keep it still. The other end is we keep hold of, and we're going to slowly stretch it out. And what's going to happen is every second we're going to stretch it out to be longer. So say it starts off as 1 metre long, the piece of string. At the start of the first second, we're going to pull it to 2 metres long. As 1 second has passed, we're going to then pull it so another metre is added. And then every second after that, we're going to add 1 more metre to it. In between those things, the snail is going to crawl along at a constant pace of 1 centimetre a second. So we pull it out to 2 metres, the snail then moves 1 centimetre forwards. We then pull it out so it's 3 metres, and the snail moves another centimetre forwards. And we keep doing that. And the question is, can the snail ever reach the end? And the surprising thing is that it can. We're going to show it mathematically in a minute, but the intuition is, when we're pulling it, if you imagine the snail is already some way along the piece of elastic band, then some of the extra distance we're giving to the elastic band is going to be going behind the snail. Imagine when it reaches the halfway point, every metre that we add on, we're only adding 50 centimetres between the snail and its target, because the other 50 centimetres is going behind it. Now we're going to prove it for any distances. So it could be the snail is going 1 centimetre and the elastic band is going 1 kilometre a second. And it's still true, it just takes a phenomenal amount of time new. Let's put some letters on it so that we don't have to use specific numbers. We'll say that the length of the elastic band when it starts is L. We'll say that every second the snail is going to go some distance, so we'll call it D maybe. And at the start of every second we're going to add on an extra piece of length. And so that piece of length there we're going to call the extension E. We're going to define a piece of notation here, and I'm going to use the same notation here as Wikipedia uses, so when you go and look it up, it won't be too confusing. They use theta of n for, at time n, what proportion of the elastic band has the snail gone. So, for example, when the snail first starts, theta of 0, so at the first time, the snail has gone no distance, so as a proportion of the whole distance, it's gone 0. What we're aiming for is to get theta of n up to 1, which would mean it's gone the whole way along. So theta is something that varies between 0 and 1. Okay, well, we can say what theta 1 is. Theta 1, so at the very start, we pull out the extension. So the length of the piece of elastic band is now L plus E. And then the snail goes 1 distance D along it. So as a proportion of the whole elastic band, it's gone D out of L plus E. So as a proportion of its way, it's gone that proportion. Okay, well, at the end, as it gets to the end of its D distance there, we pull the elastic band out, but actually it keeps the proportion where the snail is in the same place, because some of the distance is being added behind it, some of it's being added before it, most of it, but it's in the same proportions. So just after we do our expansion, that proportion is still true. The snail then moves an extra piece of distance. So theta of 2 is the proportion you already did, because that's preserved, D plus L over E, plus an extra bit. And that extra bit is, it goes D distance again, but now the overall length is slightly more. It's now L plus 2 lots of extension. And this thing just extends. So theta of 3 would be that bit plus D over L plus 3E, and it carries on like that. So I'm just going to adapt this one to be the general one. If we made that n, then that would be there, plus dot dot dot, plus d over L n e. We've just got a sequence, a series there, with all the terms added together, going up to this term here. Now we're going to make use of a little identity here. The idea is, I'll do it up here, if we had something d plus L plus ke, some general amount there, some general way along this, these are actually greater or equal to d plus kl plus ke. Me putting this extra k in, because for any k which is 1 or bigger. Because if we do this times here, because these are all positive numbers, this denominator gets bigger, so the overall fraction gets smaller. It's only equality if k is 1 in this case. Or L is 0, I suppose. But this thing over here is, we can take out a k, we've got d over L plus e times 1 over k, which is going to be quite useful here. The idea is we can use that identity on all of these going along, so we can say that theta of n is greater or equal to, and then we can take out a factor of these. So d over L plus e, and we can take out each of these going along. We're going to have 1 over 1 plus 1 over 2 plus 1 over 3 all the way up to 1 dot 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 1 over n. This thing here. Okay. But these things here are just constants. This is just a constant here. So if we can prove that this thing doesn't tend to 0, because these are all just nice positive numbers, then if we can prove that this is growing, then this thing will definitely get to at least 1. But actually this thing here is quite a famous thing in mathematics. It's called the harmonic series. And we know for a fact it's bigger than 1. Okay, we'll prove it. So, well, we definitely know it's bigger than 1. We can prove for a fact that it's growing. So this thing here is 1. This thing here is a half, just this one. These things here are both bigger than quarters, so together make a half. If you took the next 4 terms, they're all bigger than an eighth individually, which add up collectively to a half. If you then take the next 8 terms, they're all bigger collectively than the 16th, and so will add up to a half. And you can carry on that pattern, and you just get a whole lot of halves added together, which adds up to infinity. So this whole thing tends to infinity, so this definitely gets to at least 1. And that's the idea. Once we've got that theta of n is greater or equal to 1, well actually, when it gets to 1, we've done the whole proportion, and so we've got that. And so, no matter how slow the snail is, and no matter how massive you make the extensions on the elastic band, as long as you're not accelerating the elastic band, as long as it's only doing the same distance each time, then the snail will always get there. But the amount of time it takes is often astronomical. Okay?